Okay, now this is what I was going to talk about before, and I got myself carried away. So with chemical reactions, we can actually write word equations, but we tend to work in symbols because it's just a shorthand. But importantly, Lavoisier caused us to balance them. So, talked about Lavoisier before. Matter neither created nor destroyed, rather simply transferred or transformed. And it's because of his day job, the fact he's an accountant, that allowed him to recognize that all the reactants had to have gone somewhere in the products. So, well, there we are there. Lavoisier realized it's meant that every atom you start with, you should be able to account for, it has to have gone somewhere. So it's balancing the books, it's doing the bookwork. He was actually quite famous because it was first to disprove a thing called phlogiston theory. People weren't too sure really why things burnt. And interestingly enough, often when you burn something, it actually gets heavier. So that this theory was that phlogiston was added. He worked out it was actually oxygen required to burn the substance and then being added to that substance. And so the substance became heavier because of that. That's why it's so famous. But for us, it's even more famous because he worked out how to balance equations. So unfortunately, you should be able to write a balanced equation for every chemical reaction. So they get quite complex. I'm going to give you a simple one just to explain how it works. When you get to sort of year 10, year 11, if you're doing chemistry, you'll do some more complex stuff. So first of all, you need to list your reactants, the things you're putting into the experiment, into the chemical reaction, and then you should be able to list all the products. But importantly, you need to know them atom by atom. This is why you need to know the chemical formula of the compounds. You can't do this with mixtures. So it's really about accountancy. The reason Lavoisier lost his head. So, a nice easy example. Our word equation, hydrogen gas and nitrogen gas combine to form ammonia, another gas. Now, in its unbalanced form, we know hydrogen exists as H2 in the atmosphere, hydrogen gas. Nitrogen gas exists as N2 in the atmosphere, and ammonia is another gas that exists quite naturally as NH3. So hopefully you can see a problem here. I've got 2 hydrogens and 2 nitrogens in my reactants. But now I've got 3 hydrogens and 1 nitrogen in my product. Lavoisier would be extremely unhappy because his books aren't balanced. So how do we balance them? It's actually not that difficult. We have to play around numbers. I can't change that detail, right? That's the molecule, that's the molecule, that's the molecule, that's how they are. But I can change the number of molecules. So if I go with 3 hydrogen molecules, I end up with 6 hydrogen atoms. I only need 1 nitrogen, and now I have 2 molecules of ammonia. That means I've still got 2 nitrogen, 2 times N, 2 nitrogen. I've got 6 hydrogen here, 2 times that 3, we've got 6 hydrogen this time as well. So this is how you have to go. Now this is a simple one, right? Obviously you can get very complex chemical equations, and balancing them out can become quite difficult. We don't have to worry about that just yet. Just here's an idea of what's required. The other thing we should be aware, of course, is reaction rates. So chemical reactions can occur at different speed, and we can control it. Often we want to control its speed. We don't want the bomb to go off and waste all its energy straight away. You might want it to explode slowly over a period of time, or whatever the experiment might be. You might be trying to control what's going on. So temperature is important, like everything. The more energy you put in, the faster the particles can move, so the faster the reaction will take place. You want to slow it down, the easiest thing to do is cool it. Right? Take energy out. Concentration of reactants, so how concentrated is your acid or whatever reactant you're using. How much, in a sense. The size of the particles. So we break them right down. So here's sort of a bit of gravel becoming a bit of sand. Silt and clay are even smaller. So I can break that sand up and cause it to become silt, or take an object like that and make it into lots of small objects, there's more space for iteration to take place. So that will get faster. Or we can use a thing called a catalyst. It's a chemical that actually helps get an experiment running faster. And we're done again.